So in this video we're going to be talking about how to utilize the attribute of self-similarity when dealing with these sorts of problems. For example, in the case of the first one, this infinite continued fraction, we have already seen that this denominator is the very same as the entire expression, and we could exploit this attribute to calculate the value of this infinite continued fraction, which was 1 plus square root of 5 divided by 2. Now, let's just look at this equation, for example, and if we can use similar ideas in this problem. So we are looking for a real number which we tetrate to the plus infinite, and we are getting 2. Now, what's going to be this real number? Now, what we can immediately observe that this exponent is the very same as the entire expression, which has a value of 2. Therefore, we can substitute this exponent with 2, leading us to this quadratic equation. And it's x squared equals 2, and it can be solved pretty easily. It's going to have these two solutions, plus minus square root of 2. And what it says is that if this equation has a solution, then it should be either plus square root of 2 or minus square root of 2, leading us to this identity here below. Now, let's just look at the third example here, and we would like to calculate what's going to be the value of 2 to the power of plus infinite, which is defined as the limit of this sequence, so this 2 to the n sequence. And one might intuitively think that it's going to tend to plus infinite for a good reason. And let's just assume for a second that this sequence converges to a real number, and we're gonna denote it by lambda. And again, use the self-similarity idea, just like in the case of the infinite continued fraction. This expression is lambda. Therefore, we can substitute this one with lambda, leading us to this equation, this linear equation in lambda, and the only real solution of it is lambda equals 0. And this might suggest that if we multiply 2 by itself infinite amount of times, then eventually we get 0. Now, just remember for a second that in the beginning of this calculation, we presumed that this sequence converges to a real number. Now, what we have to consider now is that we can talk about convergence in different concepts of distance. For example, we can talk about Euclidean distance, and obviously in Euclidean distance, this sequence will hold to plus infinity. It's going to be a divergent sequence. But in P-adic distance, this sequence will converge to 0. Now let's look at these two concepts of distance. So the Euclidean distance is generated by the Euclidean absolute value function, and similarly the P-adic distance is generated by the P-adic absolute value function. And the P-adic distance of two numbers is given by this formula, 1 divided by p to the psi p a minus b, and this psi p a minus b is the exponent of p when we are talking about the prime factorization of a minus b. And in the case of the Euclidean distance, well, Euclidean distance is the same concept as a layman would think of the distance. Well, it can be defined in a myriad of different ways. For example, the maximum of a minus b and b minus a. That's only one example of how you can define this Euclidean distance. There are definitions, for example, which involve the sine function. Well, just look at some examples of how this Euclidean distance compares to P-adic distance. For example, what about 10 and 2? In Euclidean distance, they are 8 apart from each other. But in P-adic distance, we have to consider the prime factorization of a minus b. So just talk about the prime factorization of 10 minus 2. And in the prime factorization of 8, the exponent of 2 is 3. Therefore, the two-adic distance of 10 and 2 will be 1 divided by 2 to the 3. That is 1/8. Now let's look at another example, 101. The Euclidean distance is obviously going to be 99. But to calculate the two-adic distance, we have to consider how the prime factorization of 99 will look like, and what would be the exponent of 2 in that prime factorization. Now, 2 does not divide 99, therefore this exponent will be 0. So what we're getting is the two-adic distance of 101 will be 1 divided by 2 to the 0, which is 1. Now, it means that certain numbers can be very far apart from each other in one distance, but in another concept of distance, they can be very close. Now, this gives us an intuitive idea why these sorts of sequences can converge in one concept, but cannot converge in another concept of distance. Yeah, so the distance of 2 to the n and 0 in the two-adic distance is going to be 1 divided by 2 to the n, which obviously tends to 0. But this distance in Euclidean distance is going to be 2 to the n, which is not convergent. And a very profound example would be this geometric sequence is the sum of q to the n when n goes from 0 to plus infinity. So this 1 plus q plus q to the second power plus q to the third power plus forever and ever. It's 1 divided by 1 minus q when the absolute value of q is smaller than 1. But if we are opting for not a Euclidean distance, but a P-adic distance, then obviously this kind of idea changes, that we are looking for a q value whose P-adic norm is smaller than 1. And in this concept, for example, the two-adic norm of 2, so the two-adic distance of 2 from 0 will be 1 divided by 2, which is obviously smaller than 1, meaning that this sequence will converge in that concept of absolute value, or in that concept of distance. So 1 plus 2 plus 4 plus 8 forever and ever will converge to 1 divided by 1 minus 2. The only thing I did was that I substituted q with 2, and therefore this value, this limit, will be minus 1. It means that if I add the powers of 2 from 1 to forever, eventually I get minus 1. And there are some other examples of this depicted in this picture. Now, so what we can learn from this is that convergence depends on what kind of absolute value and therefore what kind of distance I opt to utilize. So, for instance, if I add the powers of 7, eventually I get minus 1/6. Thank you so much for watching.